video, I want to walk through the review of some math concepts that will be relevant for General Chemistry 2. Specifically, we're going to talk about exponents and logarithms or logs. We'll talk a little bit about the quadratic formula and another method of solving polynomials called successive approximations. We're going to start with just the idea of exponents, which hopefully most of you who are watching this are pretty familiar with. So when we have a number raised to a specific exponent or power, like a to the m, for example, that just means we are multiplying that number a m times, right, by itself. So for example, a to the third would just means a times a times a 3 times, or a to the 7 would mean that you do it 7 times. If you multiply two numbers that both have the same base, which is a in this case, but different exponents, then it's the same as adding those exponents together. So for example, a to the m times a to the n is the same as a to the power of m plus n. If you do the division of two numbers with the same base but different exponents, that division just means that you are subtracting one power from the other one. If you are raising a number with an exponent with another exponent, then it's the same as multiplying those two exponents together. So for example, a to the power of m raised to the power of n is equal to a to the power of m times n. These hopefully are properties that you're pretty familiar with. Now we're going to use those properties and apply them to logarithms or the log functions. And so logs are just the inverse of exponential functions. In fact, some of the components that we see in exponents come back in the log function. So if you say a to the power of m is equal to this number b, then the log with base a, so a is our base number here, the log of base a of b is going to be equal to the exponent. So b here is what I call the argument, a is the base number, and then m is the exponent. So as you can see, it's the same three numbers. We are just relating them differently in the definition of log. So for example, let's say you have a base 10, the number 1000. Well, that means your question is, what is the power of 10 that will give you 1000? And the answer is going to be 3, right? So log 10 of 1000 is that going to be 3. Just as a note, base 10 is usually not written, so you'll just see log of 1000 equals 3 most often in applications. In other bases, you will see the base number being written. So here, for example, if you have log with base 2 of 16, then you'll see that that should equal to 4 because 2 to the power of 4 is equal to 16. There is a key usually in your calculator called the log key that you can use to do these type of operations. So here I'm showing the TI-30X calculator, which is the one that we use at the college I'm teaching, and that one has a log key in it. And if you want to do exponent, you just have to press that second and then the same log key, which actually gives you the exponent operation or 10 to the power x operation. So it's just the same key but two different functions. Now, one of the most important things in chemistry is the log base e. So e is a number. The value is 2.71828 and it keeps on going. So it's one of these numbers that was discovered in math but turns out to have many applications in the natural sciences, so biology, chemistry, or physics. The number e keeps popping up, just sort of like pi is another number that kind of pops up a lot in various applications in the natural sciences and in math. So log base e is what we call natural log. So a lot of times, instead of writing log base e, it would just be written as ln, which stands for natural log. So if I write log base e of the number 7.389 as my argument, I'll find that that's equal to 2. That's because e to the power of 2, or e squared, is equal to 7.389. Another way to write this would be to say ln of 7.389 is equal to 2. Now, if you do other powers of e, so like in this case, if you do e to the power of 3, you get 20.0855, or therefore if you take ln of 20.0855, you should get 3. The ln key on this same calculator is just right below that log key. So if you want to do an ln operation, all you need to do is you put your ln key and then put the numbers in, like ln of 7.389, and it should give you 2 as your answer. If you want to do e to the power of a number, then you would do second and then the ln key, and that will do the e to the x operation. So here's an example you can all try if you have this calculator or something similar to this. You do, let's say the question is ln of x is equal to negative 1.5, right? So what's the value of x? So in this case, again, the idea is that e to the power of negative 1.5 is going to be equal to x, right? So punch in our calculator here, second, and then the ln key that would result in the e operation, and then you then punch in negative 1.5 and press equal, you get this answer right here, 0.22313, and hopefully you can do this with your calculator that you're using in your school. As I said earlier, there's a number of applications, not just in chemistry, but also in biology and physics, where log functions become useful to use. So for example, if you have a large range of numbers that are all multiples of 10, using log base 10 would be useful in creating a scale. So there are several examples of these scales. In chemistry, we have a measure of acidity that we call the pH scale, which relies on multiples of 10 of the concentration of H plus or proton, which is the measure of the strength of an acid. In physics, we have measurement of the loudness of sound in decibel, which is also given in multiples of powers of 10. In earth sciences, we have magnitude of earthquakes measured in the Richter scale, which again is given as powers of 10. So if you say an earthquake is Richter scale 3 versus 6, it's not just a doubling, it's actually 1,000 times stronger, right? Because it's 10 to the power of 3. That's the actual difference between those scales. So that's one application. The other application we often see is in using natural log, as I mentioned earlier. Say, for example, in chemistry, decay of radioactive isotopes. That turns out is very much following the form of the ln function. Cell growth in biology follows the ln function as well. Even in business, where you calculate compound interest, or in finance, I should say, you can use the ln function to model the amount of principal that you will get after an X number of years. And so there is a lot of applications of these two functions. So here I just want to show you what these functions look like when you plot them. The blue one here shows the exponential function y equals e to the power of x. You can change the shape of this function by adding a couple of additional numbers to this, which we'll talk about later. So if you have a constant here, let's say we put a constant a here in front of the e to the power of x, that's going to change how this curve is going to be shaped on the xy coordinate. If you put another number here next to the x, so e to the power of bx, for example, that number b, that constant b, is going to also change the shape of this exponential function, okay? The log function is just the inverse of this, as we said earlier. So the natural log of x will look like this, which is kind of the mirror image of that exponential function. And you can see that the green line here shows the line equation, y equals x, which is kind of like the mirror of these two inverse functions. Now, what we want to do is understand a little bit how to operate with logs, because there's several derivation of equations you'll see in general chemistry too that will require you to know properties of log. So properties of log, a lot of them are associated with similar properties in exponents that we talked about earlier. So there is an addition property. You recall that in exponents, when we add the exponents together, that's the same as multiplying them. So here is the same idea. You add two logs, it's the same as taking the log of the product of those two numbers, so multiply the a and b together. Here's a quick example. If you take the log of 10 plus the log of 100, and the log of 10 is just 1, because remember 10 to the power of something equals to 10, so that's 1. Log of 100 is 2, so the answer here is 3, right? But we can also write log of 10 plus log of 100 as the log of 10 times 100, which is the log of 1000, and the log of 1000 is also 3. So as you can see that these two expressions is equal to that expression. The subtraction property, similar to what we see in exponent, when you subtract things together, is the same as doing a division. So if we do log of a minus log of b, it's the same as taking log of a divided by b. So here that example again with log of 1000 minus log of 10, log of 1000 is 3, log of 10 is 1, so 3 minus 1 is equal to 2. But you can also say that log of 1000 minus log of 10 is the same as log of 1000 over 10, which is log of 100, and log of 100 is also 2. So that shows you an example of that particular relationship. The power property, this is kind of unique to logs. So if you take the log of a to the power of b, it turns out that you can write this as b times the log of a. So here's a quick example of that property. Log of 100, as we know, is equal to 2. Now, we can write log of 100 as log of 10 squared, right? And then if we use the power property, we can take that 2 and put it back here, so it becomes 2 log 10. 10. Well, log of 10 is 1, so 2 times 1 is equal to 2. So you can see that gives you the same exact answer there. The last one I want to talk about is something I call the identity property of log. Not sure if that's the same thing that mathematicians will call it, but that's what I call it. This is just saying that if you have the same base number as your argument, then the exponent has to equal 1, right? So the log of base x of x should equal 1, just because x to the power of something equals to x, and that power has to be 1. So for example, if I do this with the natural log of base e of the number e, which is the same as writing ln of e, should equal to 1, right? So that's the identity property.